Lesson 4 is called sequences, and in 4.1 we're just going to get into like what a sequence is. So starting in the upper left corner, many beautiful parts of nature are examples of mathematical patterns. In fact, many follow the same pattern, the golden ratio, which is determined using the Fibonacci sequence. The spiral of a seashell, the seed head of a sunflower, and even the ratios for different parts of the human body are all related to the Fibonacci sequence. So a sequence, not just Fibonacci, but a sequence in general, is a function whose domain is the natural numbers. And the natural numbers are like the numbers that you count with. So all positive numbers with no decimals or fractions or anything like that. So the set of natural numbers would be like 1, 2, 3, 4, and so on. It would go up forever, but it wouldn't go down at all. So it's all of the like positive whole numbers. And then Fibonacci sequence is 0, 1, 1. It's not a typo, there's 2 1s. 2, 3, 5, 8. So 0, 1, 1, 2, 3, 5, 8. And that pattern will continue forever. And this one, like, I personally find it like kind of hard to recognize the pattern the first time. The like 2 1s throws me off. So it's not like you're adding the same amount each time. So the way that you get a number is by adding the 2 previous numbers. So like we would add 0 and 1, and that would be 1. And then to get the like 2, it's because we added the 2 previous numbers, the 1 and the 1. And then to get the 3, it's because we added the 2 previous numbers, the 1 and the 2. And to get the 5, we added the 2 previous numbers, the 2 and the 3. And then to get the 8, we added the 2 previous numbers, the like 3 and the 5. So that means to get the next number in the sequence, because it does go on forever, we would have to add these last 2 numbers, like the 5 and the 8. So 5 plus 8 is 13. So if we're asked to find the next number, it'd be 13, because we're adding 5 and 8. Okay, so example 1, write the first 5 terms of the following sequence, then write the first 5 terms as ordered pairs, which are like points that you would put on a graph. So the first term is 5, and then to find the next term, you would subtract 2 and then multiply by 2. So the first term is 5, so we'll just say, I'm just going to list them as first term is 5, and then to get the second term, I think I'm just going to write it as first, second, and third just to save some writing. If you want to leave like term next to first, you can, but move too much over. Okay, so the first term is 5, and then for the second term, it says that we need to take our first term and subtract 2 and then multiply by 2. So that's going to be, we'll take our previous term 5 and then we'll subtract 2, and then after that we'll multiply by 2 and we'll simplify that. So we're taking like our first term, or like the one right before the second one, and then we have to take that one, subtract 2, and then multiply by 2. So if we do 5 minus 2, that's 3, and then we have to multiply that by 2, so 3 times 2 is 6. So that means that the second term in my sequence is going to be 6. And then to get the third term, we have to take the previous term, which this time it's 6, and then we have to subtract 2 and then multiply by 2. So 6 minus 2 is 4, and then I have to multiply that 4 by 2, and that would be 8. So the next term in my sequence would be 8, and then to get the fourth term, I would take that previous term, the 8, and subtract it by 2 and then multiply by 2. So 8 minus 2 is 6, and then if I multiply 6 by 2, that's 12. So my fourth term is 12, and then I'm supposed to find the first 5 terms, so I have to do this one more time. So the fifth term, I would take the previous term, the fourth term, the 12, and subtract it by 2 and then multiply by 2. So 12 minus 2 is 10, and then 10 times 2 is 20. So my fifth term is 20. So just to kind of run back through that and summarize really quick, it said that the first term was 5, and to get the next term, we have to subtract 2 and then multiply by 2, and we continue that pattern to get each like consecutive term. So we started with 5, and then to get the second term, we took 5, we subtracted 2, and then we multiplied by 2, and then we got 6. So then to get the next term, now I did 6 minus 2, and then multiplied by 2, and that all together equaled 8. And then to get the next term, I had to take 8 and subtract 2, and then multiply by 2, which gave me 12. And then to get the next term, I had to take 12 and subtract 2, and then multiply it by 2. And that gave me 20, which is my fifth term. And then now, the second part of the instruction says to write it as like an ordered pair. And when we list terms in a sequence as ordered pairs, actually, hold on, I'm going to backtrack a second. So if we wanted to write this as like kind of like a set, like how a Fibonacci sequence is, with those like little brackets, we would write it with those little like curly Q brackets, and then we just list them in order. So the first term, not necessarily like highest number to smallest, but we'd start with the first term, which is 5, and then the second term, which was 6, so 5 and then 6, and then the third term, which was 8, and then the fourth term, which was 12, and then the fifth term, which was 20. But the sequence doesn't stop there. Like, we could keep doing the pattern if we needed to. So to show that in the set, we're going to write like a dot, 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 showing that it goes on forever. So the sequence is 5, 6, 8, 12, and 20. And then now if I wanted to write it as like a set of ordered pairs, I would have to kind of think in terms of like my knowledge of functions, and the input is going to be like my set number. So up here, how it says like the domain is the natural numbers, well, the input is going to be the term number and the output is going to be the actual value. So what that means is like, this is term 1, the output is 5. This is term 2, the output is 6. This is term 3, the output is 8. I don't know why I wrote 8 there, but the next one is term 4, the like actual term, like the value, the output is 12, and then the next one is term 5, and the actual value or the output is 20. So that's how we're going to write our points now. So for like our ordered pairs, it'll be 1, 5, because the first term is 5, and then 2, 6, because the second term is 6, and then 3, 8, because the third term is 8, and then 4, 12, because the fourth term is 12, and then 5, 20, because the fifth term is 20. And then if you want to leave a little note so you can kind of refer back to it, for like our points, in parentheses, I'm going to say this is the term number, like first term, second term, third term as our first number, and then the like second number, the y value, would be like the term value, like what the actual term was. So term number is first, and then term value is second. Okay, so example 2, describe the pattern of the sequence. This one was describing it in words. So the sequence itself is 2, 13, 24, 35, and 46. So we want to look at it and like see what is happening each time, like what change is happening, and is that consistent change happening all the way through the sequence. So the like kind of easiest one to check first is like if we're adding or subtracting something, or potentially like multiplying or dividing by something. So we'll check first, like if we're adding, to get from 2 to 13, we're adding 11. And then to just make sure that that's the pattern, we have to continue to see if that keeps happening all the way through the sequence. If it happens differently later on, we can't say that that's the pattern because it would need to apply to all the numbers. So to get from 2 to 13, you add 11. To get from 13 to 24, you also add 11. To get from 24 to 35, you add 11. And then to get from 35 to 46, you also add 11. So because that like kind of pattern or rule of like adding 11 worked every single time, then we can confirm that that's the pattern. So the way we're going to write it is we're going to like say what the first term is and then how we get to the next term. So we'll say the sequence begins with 2 because that's the first term in the sequence. So the sequence begins with 2. And then our pattern that we found was to add 11 each time. So we'll say and the pattern is to add 11 to the previous term. So the sequence begins with 2, that's the first term in the sequence, and the pattern is to add 11 to the previous term. So to get to 13, we added 11 to 2. To get to 24, we added 11 to 13. To get to 35, we added 11 to 24, and so on. Okay, moving on to example 3. So a sequence can be described by a function as well. So this is read as f of n equals 6n minus 3, and it asks us to find the first 3 terms of the sequence. So what that means, the first 3 terms would be n equals 1, n equals 2 for the second term, and then n equals 3 for the third term. So we're going to kind of evaluate the function 3 different times to find the first 3 terms. So first we'll find f of 1, and this is just like evaluating functions regularly. So f of 1 means that I take 1 and I put it in the function where the n's are this time. We don't have x's, but we have n's for term number. So f of 1 equals 6 times 1 in for n, and then minus 3, and then now we just need to simplify. So 6 times 1 is 6, and then minus 3, remember we would simplify like multiplication before it's subtraction, and then after that 6 minus 3 is 3, so f of 1 is 3. So that would be the first term in the sequence, is that 3. So I'm going to leave a note as well that this is that 3 is the first term because we found f of 1 and n is the term number. So 3 is the first term, and then we'll repeat that process to find the second and the third terms. So next we'll find f of 2, and that means that 2 goes into the function where n is. So f of 2 equals 6 times 2 instead of 6 times n, and then minus 3. And then we will simplify the multiplication first. So 6 times 2 is 12, and then minus 3. And then now we can subtract 12 minus 3 to get 9. So we'll say f of 2 is 9. And that f of 2 equals 9, that means that 9 is the second term. So 3 was the first term, 9 was the second term, and then the last one we needed to find was the third term, so we'll find f of 3, which means that 3 goes into the function where n is. So it was 6 times n, so it'll be 6 times 3, and then minus 3. So we'll simplify the multiplication first, so 6 times 3 is 18, and then minus 3, and then 18 minus 3 is 15, so f of 3 is 15, and that means that the third term is 15. So third term is 15, and then if we kind of wanted to write our sequence as a set now, the first term is 3, the second term is 9, the third term is 15, and then it would continue on after that. We just only need to find the first 3, so we'd put a dot 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 and then close it with those kind of funky brackets. So the sequence goes 3, 9, 15, and so on. Okay, moving down to 4.2. So the name of 4.2 is arithmetic sequences, and sometimes this word is read as arithmetic, like math, but when it's used as an adjective, in this case it's describing a type of sequence, it's arithmetic. So it's kind of different. Okay, so in the upper left corner, an arithmetic sequence is a sequence of numbers in which each term in the sequence is produced by adding a common difference d to the previous term. But the big thing to know here is that you are like adding a number each time. So when I say adding, it can look like subtracting, so because you could be like adding a negative number. What it can't look like is like multiplication. So arithmetic means that you are adding a consistent number each time, whether that number is positive or negative. Okay, so right here, this is an example of an arithmetic sequence, and if we want to find the common difference d, we just need to figure out what is like being added to each term to get the next term. So there's a couple different ways that you could do this depending on like how like simple your numbers are. On this one, it's pretty like straightforward if we just say, okay, well, to get from 5 to 8, I would have to add 3. And then to get from 8 to 11, I would have to add 3 again. To get from 11 to 14, I would have to add 3 again. And then to get from 14 to 17, I would add 3 again. So that like plus 3 that we're doing each time to get to the next term, that's d. That's the common difference. So we would say d is 3. If it looked like we were subtracting number each time, d would be negative, that's okay. If you ever have like kind of funky like numbers to deal with, you can always take one term and subtract the term before it to get d. So like if I use the 5 and the 8, I would subtract the one in front minus the one behind. So 8 minus 5 would be 3, and that would be another way of getting the common difference as well. But you only really need that if like you can't tell what you need to add to get to the next term is all. Okay, so d is the common difference, it's 3. And then for the next section, we're going to determine if the following sequences are arithmetic sequences or not. So basically, do they have a common difference? Is there something that we're adding like each time to get to the next term? So for the first one, it's 5, 2, -1, and 4. So to go from 5 to 2, we're going down 3. So that's the same thing as adding -3. So it still can be adding even if you're going down. It's just you're adding a negative number. And then to get from 2 to -1, we're going down 3. So it's like we're adding -3. And then to get from -1 to -4, we're adding -3 again because we went down 3 each time. So because we went down by a consistent amount each time, down 3, down 3, down 3, that means that yes, it is an arithmetic sequence. So you don't always have to like add a positive number and go up. The important thing is that you're adding the same number each time, and in this case, we're adding 3 each time. So yes, this one is. And then for the second one, if we're checking for arithmetic, we're seeing if you're adding a consistent amount each time. So 1, 2, 4, 8, from 1 to 2, we would add 1. And then from 2 to 4, we would add 2. So that's already like breaking it, like you're not adding the same amount each time. So that one would be not an arithmetic sequence. And it is a different type of sequence because like you may notice the pattern is like to go from 1 to 2, you're multiplying by 2. And then from 2 to 4, you're multiplying by 2 again. And then from 4 to 8. But arithmetic is strictly like an addition type of sequence, and that can show up as something that looks like addition or subtraction if you add a negative, but it's not multiplication or division. Okay, and then for the third one, it's 1, -1, 1, -1. So like to go from 1 to -1, we go down 2, and then to go from -1 to +1, we'd go up 2. So 1 is like -2 and 1 is +2. So already, since those are not the same like number for d, that would not be an arithmetic sequence. And then for the last one, -10, -5, 0, 5, and 10, to go from -10 to -5, that would be going up 5. From -10 up to -5, it's like less negative. And then -5 to 0, we'd be going up 5. And then 0 to 5, we'd be going up 5. And then 5 to 10, we'd also be going up 5. So we're going up 5 every single time. So since we're going like adding a consistent amount each time, then yes, this one would be an arithmetic sequence. Okay, moving down to the next section. This is still in 4.2, but reading off right here, arithmetic sequences can be expressed in real life situations. They end up showing up as something that's linear. So Sue puts $5 in a coin bank, and each week she adds an additional $5. Write a rule for this sequence and use it to find out how much Sue saved on the 8th week. So we'll write a rule and we'll analyze the graph. So if she is starting with $5 in her coin bank, she's going to start with 5. And then for like each week that goes by, she's going to put in an additional 5. So we'll add another 5, but it's another 5 like per week. So I'd be like times like n or x, and I'm going to say n for like the term number or the number of weeks. So 5 for the initial $5 that she puts in. And then 5n is going to be the $5 that she adds each week. And n is the week number. And then write a rule for the sequence. So I'm going to just kind of like close it out and like put it in function notation. So to do that, I'm going to write it as f, and then it needs to be of n, since n was the variable that we used for like week or term number. And then to make it be like a little bit easier to compare to the graph, I'm going to put the 5n part first, and that's going to be in slope-intercept form, which is something we talked about a bit in first semester. So it'd be f of n equals 5n plus 5, and that's something I want you to like get comfortable with as well. Most of the time when we write functions, we would put like the n part first and the constant part second. So it'd be f of n equals 5n plus 5. And then the function is graphed here on the right. All these points have kind of already been found for us. So this is saying after like at 1 week she has $10 because she has that initial like $5, and then she saved another $5 for that first week. After 2 weeks she has $15. After 3 weeks she has $20, and so on. So in this graph, you'll notice that like all of the points aren't connected. And that's almost always the case when you have a graph of a like arithmetic sequence, because all of the like term numbers are the x values. So like term 1 is the same thing as week 1 in this case, and term 2 is the same thing as week 2 in this case, term 3 is the same thing as week 3, and so on. And you can't have like term 1.5 or term like 2.5, because we talked about how these sequences, their domain is only positive whole numbers. So 1, 2, 3, and so on. So that's why the graph is not connected. We've talked about this like in the domain and range section. This is called a discrete graph. So when like all the points are separate and they're not connected with a line, it's called discrete. And then just keep in mind, anytime you're graphing an arithmetic sequence, the same thing we kind of referenced up there, the like x coordinate would be the term number. In this case, it's representing the week numbers, like term 1 is week 1. And then the y coordinate would be like the term value. So if we look at, sorry, I had to squeeze that in there. But if we look at like 530, so that means like term number 5 or week number 5, she will have saved $30. Okay, so moving down to 4.3. So 4.3 is reading recursive formulas, which there's like kind of two different like types of formulas in this unit. It's recursive and explicit, so this is recursive. So before we get into that, we just kind of want to talk about like how to read like sequence terminology, which is something that's new. So in the upper left, when working with a sequence or working with sequences, and there's this like A with a little N right there. When you hear me read that, I'm going to read it as, A, and then I'm going to say sub for short, and then N. And what I'm trying to say is A with a subscript of N, which a subscript is like a little, like this little small, it could be a number or a letter, but it's like written to like the lower right of a original letter. So you'll hear me read that as like A sub N is how I would say it. So that's what I'm reading. And then it says it refers to the nth term of a sequence, which nth term is like a math way of saying any term number. So if we kind of pull all that together, like A with the little 1, I would read as A sub 1 is the first term. The little subscript next to the A is telling you the term number. So A sub 5 is the 5th term, and A sub 30 is the 30th term. So this little guy right there, the N, is the term number. And then even like kind of in a more general, when we don't actually know the term number, there's a few other ones here that like are really helpful to know. So A sub n minus 1 is referring to the term that comes right before A sub n, that's probably the most confusing part, these two. And then A sub n plus 1 is the term that comes right after A sub n. So like, let's say for example, and you don't need to write this, I'm gonna erase it. Let's say A sub n is like 3. Well, then I would put like a 3 in for both of these, and the term that came right before A sub n or an would be A2, and the one that came right after would be A4, because you'd be like adding 1 or subtracting 1 to the term number. Okay, so example 1. The following is a recursive formula for a sequence that starts with 8, and the pattern is to decrease by 3. So this part right here, A1, that's the first term. I think I need to zoom in to be able to write this like more neatly. Okay, so A1, I'm just going to zoom way in, and then we'll zoom back out when we get to the actual problem. But A1 is the first term. I don't know how much this is helping, but the first term as far as like the neatness, but A1 is the first term, which is 8. And then for the second part of the formula, like that second line, the AN is the term that you're looking for. So AN is like the term you are looking for. I'm just going to shorten it to term looking for. And then for the A with like the little subscript of n minus 1, like this one, it's the previous term, or it's like the last term. Sorry, last is not a good word to use there. Previous term is better. So A1, that's the first term. AN is the term you're looking for. So if like the problem asked you to find like the 6th term, it would be A6th. And then the like A with the n minus 1 is saying like the term before the one you're looking for. So if you're looking for like say the 6th term, then the previous term would be 6 minus 1, so the 5th term. Okay, this takes time to get comfortable with, so it's okay. Just give yourself grace and maybe make a note card. And then just know, like with recursive formulas, which is this whole section 4.3, there's always 2 parts. So this isn't like just specific to this problem. There's always like the first term is listed first, and then the rest of the rule is listed second. Okay, so for this problem, first we're going to find the A sub 6, which is the 6th term in the sequence. Unfortunately, you can't just like find it right away. You have to find like the first 6 to be able to find just the 6th term. You can't really like skip ahead. So in recursive, we're given the first term. So I'm just going to write that down. So like A1 is 8. And then to find A2, the rule is right here. So we have to take the previous term and subtract 3. So the previous term is 8, so that'll go here. And then we have to subtract 3, so A2 would be 5. And then to get the third term, that'd be A3. So to get the third term, you have to take the previous term, which was 5. It was the second term, so the 5 goes here. And then from that previous term, you subtract 3, so 5 minus 3 is 2. And then next would be the fourth term, so it'd be written as A4. And to get the fourth term, you take the previous term, which is the third term, which was 2. And you take that 2, put it right there, and then the next term you would have to subtract 3 to get. So it'd be 2 minus 3, which is -1. And then the next term would be the fifth term, A5. So to get the fifth term, you take the previous term, which was the fourth term, which was -1. You take that previous term, -1, and you subtract 3. So -1 minus 3 is -4. And then to get the sixth term, which is the last one that we're looking for, we take the previous term, the -4. So to get the sixth term, it'd be A6. We take the previous term, the -4, and we subtract 3 to get the sixth term. So -4 minus 3 would be -7, and that gives me my sixth term. So my sixth term would be, I'm going to write it over here, A sub 6 equals -7. And then for the second part of the problem, it says to list the first 6 terms of the sequence. So I'm going to go through and just kind of circle each one. The first term, A1, was 8. The second term was 5. The third term was 2. The fourth term was -1. The fifth term was -4. And the sixth term was -7. So now we just need to list them in order of term number. So term 1 was 8, term 2 was 5, term 3 was 2, term 4 was -1, term 5 was -4, and then term 6 was -7. So the sequence is, oops, I forgot my ... after because the sequence can keep going on forever. So the sequence is 8, 5, 2, -4, 8, 5, 2, -1, -4, and -7. So it's always kind of nice to double check your sequence with what the problem originally said. So it said a sequence that starts with 8 and the pattern is to decrease by 3 each time. And you can see on my sequence right here, I'm going down 3 each time. So 8 to 5 to 2, you're going down 3 to get to the next term each time. So we're all good. Okay, big thing from this problem is just if you need to find the sixth term, unfortunately you can't just skip ahead for a recursive rule. You will be able to force something called an explicit rule in the future, but for a recursive rule, you have to find all first 6 terms to get to the sixth one. Okay, and then this is the last example. So example 2, the following is a recursive formula in function notation. So it is the same thing, it's just written in a different notation. So this first part right here, f of 1, that's the first term. And then I'm actually going to zoom out so we can kind of look at them together. So that f of 1 is the same thing as A1. It's the first term. And then here is where the part's a little bit different. But f of n plus 1 is going to be the next term, or the term that you're looking for. And then f of n is that previous term, or this term that we know. So f of n is the previous term. F of n plus 1 is going to be the one that we're looking for. And that doesn't have to click a lot right now, but the hope is that once we go through the actual example, it's okay. Okay, so same thing here. Even though it's in function notation, you need 2 lines. You need the one for the first term and then the one for the rest of the terms in the sequence. So for this problem, we're going to find f of 4. So same thing applies where we have to find the first 4. We can't just skip right to 4, unfortunately. So f of 1, I'm just going to write that because it was given to us. So f of 1 was 3. That was the first line from the rule. So f of 1 equals 3. And then next I'm going to find f of 2. So f of 2 is going to be this is the rule that we like have. So whatever the previous term is goes right here. So it's going to be 2 and then times the 2 and then times the previous term. So 2 times the previous term was 3. And then after that, there was the plus 4. So the thing that's changing here is we're putting, like, if, actually I'm going to erase this really quick. You don't have to erase it. But so the rule itself is 2 times f of n and then plus 4. And f of n is the previous term. So we're just going to take out the f of n and put in the previous term, which was 3. And then we'll simplify. So 2 times 3 is 6. We have to multiply first before adding. And then 6 plus 4. So 6 plus 4 would give us 10. So now f of 2 equals 10. And then for f of 3, I'm going to do the same thing where I just go ahead and like kind of rewrite the rule. So the rule itself, and I'm referring to like this whole part right here. It was 2 times f of n plus 4, and then f of n, that was the previous term. So we got to take our previous term, which was 10, and put it in for f of n. So I'm going to erase the f of n and put 10 in there. And then we'll simplify, so we got to multiply first. So 2 times 10 is 20, and then plus 4. And then 20 plus 4 is 24, so f of 3 was 24. And then we just need to go up until f of 4. So this is the last one. So f of 4, and I'm just going to rewrite the rule again. The rule is 2 times f of n, and then plus 4. And f of n is the previous term. So my previous term was 24, so I'm just going to put the 24 in where the f of n is. So just right here. So times 24, and then 2 times 24 is 48. I got to multiply first before I add, and then plus 4. So f of 4 equals 48 plus 4 is 52. And then the problem asks for f of 4, so we can stop there. We don't have to keep going. So the final answer for f of 4 would be 52. Okay, so I definitely recognize that getting used to all these notations is not the easiest thing in the world. So I highly recommend making formulas of all these different kind of types of notations that you see these two, and kind of labeling what they mean as far as first term you're looking for in previous term, and then the same thing for the function notation version as well, because you'll see both on checkpoints in the exam.